Let's look at one example for the method of separation of variables to solve Laplace equation in a 2D domain. So examples that I have here. We want to find out the temperature distribution in solid plate where, let's assume, 3 sides are kept at 0 degree C. The right side is T1 or 250 degrees C. So what we are looking here is we have a solid plate. And 3 sides of that are at T0, which is 100 degrees C. This is T0, this is T0, and the right hand side is at 150 T1. And we'll find out the temperature distribution inside this solid. Now I can choose the axis here. If this is 0.0, I'm gonna call this one axis of X, the other one Y. And let's assume the length of this system is, this plate is L, the width of that is W, the thickness is small in the Z direction. The reason for the smallness of that is then we can deal with the 2D heat transfer in this system. So we can assume the temperature in the Z directions are uniform everywhere. So what we know here, the knowns are temperature, T1 150 degrees C, T2 100 degrees C, and K constant, or we can assume K constant. We are going to find T as a function of X and Y, temperature distribution. And in terms of assumptions, I'm going to make assumptions. This is 2D steady state, no heat generation, no radiation or convection happening around. By making this assumption, starting from the general form of heat conduction equation in the 3-dimensional Cartesian and simplifying to the 2D, no heat generation and everything, we are ended up with the Laplace equation. I didn't write down, but I strongly suggest you to start from the general form. So applying all the assumptions, we reach to the Laplace equation. Now, in order to simplify this solution, we normalize. We can normalize temperature distribution. Normalize temperature. And I can normalize the temperature here at theta by defining temperature at any point x and y minus T0 divided by T1 minus T0. And if I do the replacement in the Laplace equation, I'm gonna get d theta x2 this is gonna be the Laplace equation with the normalized temperature theta. And in terms of boundary conditions, we need 4 boundary conditions. The first one here is the boundary conditions are known temperature at different surfaces. So what we have here at the plane of, let's say, y0, sorry, at the plane of x equal to 0, but y is changing from 0 to y, this is t0. The same thing on the other plane, when x is changing from 0 to L and y0, temperature is going to be T0, and at the top is going to be T0. And here on the right hand side, when x equal to L, for any y between 0 and W, we're going to get T1. So I'm going to write down those boundary conditions. So theta of x and W, so YW, but x is changing from 0 to L. It's going to be T1. So it's going to be T0 minus T0 divided by T1 minus T0 is going to be 0. This is at x between 0 and L and y equal to W, the width of that. Similarly, theta of x and 0 is going to be 0 any x but y equal to 0. Theta of x is 0 and when x is 0 at any y is going to be again 0 equal to 0 W and 0. The last one is theta of L and y, which is going to be T1, which is T1 temperature with the T1. T1 minus T0 is 1 equal to L, y between W and 0. So these are the 4 boundary conditions that we need. Now using separation of variables, we have x double prime plus lambda square x equal to 0, y double prime minus lambda square y is equal to 0. Now, lambda square could be negative or positive. If we choose lambda square positive, we get no solution. No solution will satisfy the boundary conditions that we have, the 4 boundary conditions that we listed. So we go for the lambda equal to for lambda square less than 0. If lambda square is less than 0, then we have the solution in the form of theta of x and y is c1e to the power of minus lambda x plus c2e to the power of plus lambda x, c3 sine of lambda y plus c4 sine of lambda y. This is going to be the general form of solutions. Now, if we use boundary conditions, that we have, we can get theta x and y, which is going to be, in fact, tx and y minus t0 minus t0. And this solution is going to be 2 over pi sigma n equal to 1 to infinity minus 1 to the power of n plus 1 divided by n sine of ny over w hyperbolic sine of n pi x over w sine of hyperbolic n pi l over w. There's a pi here missing, pi. Okay. So this is going to be the general, or this is going to be the solutions after inserting the boundary conditions that will give us the temperature distribution. Now I can plot graphically the temperature distribution in this system. So let's say this was our plate. And what we had here is theta was 0, theta was 0, and theta was 1 at this surface. This was the y-axis, and this is x-axis. Now, if you plot, if you just put this one, select a few terms like N1, 2, 5, or 10 in a MATLAB or Excel spreadsheet, and then you can find the temperature at any X and Y. Now, if you plot that one, the isotherms are gonna look like this. And it can go all the way. So I'm just plotting a few isotherms here. So these are the isotherms. These isothermal lines, what they are showing here is the temperature are constant. So let's say this could be theta equals 0.8 or 0.7, 0.6, 0.4, all the way till it gets to 0. Now, we know the heat flow rates are normal to that. So if I plot the vectors of the heat flow rate, then remember everywhere we are going to have 90 degree. Ninety. Oh, it's not important. And we're going to have the same thing on the other side. It's going to be 90, 90, 90, 90. So these are heat flow lines or adiabatic lines. Remember, heat is just flowing normal to isotherms through these green lines that we have plotted here. And there's not going to be any heat crossing any of these heat flow lines. So we won't have any heat passing through these lines. That cannot happen. And that's why we have called them adiabatic lines. Actually, these lines, what they are specifying here is a surface or a line that heat does not really cross. We can have transfer of heat from one line to another line in these adiabatic lines. And that's what we call them adiabatic lines here.